So the fact that they are taking the average of several measured numbers makes this an exact number. But that, I have never ever covered that in my class.
I'm so confused.
So that's more like statistics. When you take several measurements and then you calculate an average, the mean, they call it in statistics, that number becomes an exact number. But that's ridiculous. So of course I'm gonna have to give everybody 1 point, because if you had a slightly different question or the word average was not mentioned, then I'm just gonna add 1 point standard. So what was the other one?
I think there might be one more down below the other one. This one had a lot of problems.
Okay, so
That one right there. So it was to, identify the number of significant figures. It told me that 337.0 was not 3 significant. Is it not?
it is 3 significant digits.
See, I thought it was 2, but it said that it was supposed to be 2 significant figures.
So let's see, where would that number have appeared? There. Yeah, that is definitely 3 significant digits.
I tried
without any question.
to put it in different categories, and I was like,
Yeah, it doesn't matter where you put it here or in any of these statements or any there. That decimal point, the only way it would be 2 significant digits is if it was written like that.
Yeah.
That's not a placeholder, that is a measured 0.
Yeah.
So I'll take that one also. And does that mean?
That was the only problem that I think I had any problems with.
Now what about this one right here, 2.26?
That one I think I might have just got it wrong. Oh yeah.
Well, let's take a look at this one. This is interesting. I see.
All my attempts.
This one was actually, I know.
So confused.
This is the one that is closer to the right answer.
Yeah.
Now, I mean, this is such a wonderful way of reviewing information. So when you have a number like that, 8,800 something, and you're trying to reduce it to 2 significant digits, if you reduce it to 88, well, it's no longer in the thousands. It is 2 significant digits, but it's in the is not comparatively speaking correct. So, for instance, if the population of Fall River, I have no idea what is the population of Fall River, but let's say 100,000.
It's about 100,000.
100,000. So let's say 900,000, 232 people, whatever. And I want to round up these to only 2 significant digits. I cannot say that there's 99 people in Fall River. So this number and this number are very far away as far as the dimension of the number. So to make it right, to make it in the same dimension, you have to add placeholders. So these 2 tells me to keep the 9 as it is, so there is a 9. But then I need to make sure that I'm in the tens of thousands. So I need these as placeholders. I cannot, however, put a period here because that makes that 5 significant digits. So it has to have just the zeros. So by the same token, this number right here, the 0 is telling me that I keep the 8 as it is, okay? I had to get rid of that 0 and that 7, replace it with placeholders, which they're always zeros. So 8800 should be the right answer. If the number had been 8897, and you needed 2 significant digits, what happens now? Then the one that you put in here, at 3:54, that's not too bad, it's PM. Believe me, many of you, you know who you are. That would be AM. It's amazing when when I see when you're working, it's like, oh my God, they probably just finished work. And it's 3 o'clock in the morning and they're working in this homework. Well, you have no idea. I just feel overwhelmed with gratitude, I guess is the word. So anyway, yeah, that would be that number into significant digits. Now, let me show you how easy it is to do this. So what I do is, and I had to do this, of course, for everyone this time, but I see that you have 34.66 out of 35, so the subtraction of that is what? 35 minus 34.66 is 0.34. So to not give you extra credit, I had to add exactly 0.34 points, which is down here, 0.34. And I'm gonna do that, but just give me a few days, and that changes the score. You don't have to go back and redo it unless you want to practice. And the good news is that it always takes the highest score, not the last attempt. Okay? So if you decide that you want to
Average it out, it takes the highest.
it doesn't average it out, no. It takes the highest score. So if you are happy with a 95 and you want to take it again and you think you're going to do worse and it's going to lower your average, that's not what happens. It's going to take the 95. So always use those extra attempts if you want to practice. Now, another thing that you should be aware of.
I'm sorry to interrupt you. Can you go
Yeah.
back and redo it to get a higher grade?
Yeah.
Yes, absolutely.
Oh, okay.
For the homework, you have like 5. Oh, wait a minute. This is homework? 3 attempts total. Now, every homework problem has 5 attempts per question. So 5 times 3, that's 15 attempts per question. I mean, that should give you enough time to practice and to get it right. And I know it's almost like busy work rather than thinking at one point. But, if you use it wisely, I think you can learn.
It was, I know, I started at 1:30. I think you see my last question.
Yeah, that was
Finished
at
at
3 something.
4:30. It was so
Now,
long.
let me open.
Every question had like 6 questions.
Now, this is going to be like me, not like a student. So we need to work on chapter 3 before we move to chapter 4. So let me take a look at the homework first. And there's one thing about, so I move all of the deadlines. So this is a conundrum in a way. I don't know what is going to happen. But you don't see any deadlines now until December something. Please keep on track. Now, I do synchronize the grades with certain frequency. So you should be able to see your grade when you finish your work. Pearson, I think by default, doesn't show you the grade until the deadline. But it does synchronize them with the Canvas gradebook. And there's a Canvas gradebook that you probably are aware of. You go to grades and you can see your grades. If the grade in Pearson is different from the grade in Canvas, that means that I haven't synchronized them. Once I synchronize them, they should be the same. If you ever encounter a problem with that, you just let me know. But let's take a look at the homework first.
For chapter 3, right?
For chapter 3, yes. If anybody wants to talk about anything on chapter 2, we can always do that.
Can I just ask you to share that YouTube page with them, what you shared with me? You were talking about significant figures, and you said he's kind of like right to the point. Do you remember what it was? What YouTube channel that was?
His name is
I'll look it up.
Dave
I watched
DeWitt.
YouTube,
No, Tyler DeWitt.
Tyler DeWitt.
Yeah.
I watched like all.
So
Ask
in my,
Mr. J, all
yeah.
that stuff, but he was really.
He's very good, very, very good. So in my other course, and all you had to do is ask, so thank you for asking. In my online version of this course, excuse me, because we don't meet face to face, I do have to add a bunch of videos. Sometimes they are these videos that I'm taping here, but sometimes there are videos from other people. And this guy, where is it? Oh, probably not on that module. His name is Tyler. No, that's me. No, boo. Nope. Okay, so his name is Tyler DeWitt. He has his own channel, and many of these are very, very, very good. He goes very slowly, step by step, uses examples. So I guess, and some of them go back, oh, holy cow, 16 years ago.
And they're short videos too, it's not like a big drawn out.
Right.
My page and my YouTube channel, and it's just like.
Yeah, so if you want to write down the name is Tyler DeWitt. Thank you for mentioning that. Okay. I just don't know if I'm in the... Okay, here we go. Now, one thing that you may not know, and if you already know it, please bear with me while I tell some of you who may not know. There's a print icon on the top left. Once you have finished your work, if you want to print this assignment, all you do is click there, and then, there's a number of navigation points. This opens a print view of your work, and of the quiz also, actually, before you even do it. But then, if you don't want to just print it like that, there is another navigation. I think it's on the top right. Let me see. There's another print button here. So most of you could just print that to PDF, and that would be the end of the whole thing. But if you don't want to take the trouble of doing that, if you click here, then it opens a dialog for your printer, whether it's a real printer or it's a PDF. And you can always save this document not as a hard copy, but as a PDF. So click on Destination and just choose Save to PDF. And then you'll have a copy of that assignment for you to review offline, not having to be connected. Same thing for the quiz or the quizzes. So all of them are printable. Okay, so you know what? Let me go back to the print preview and take a look at the questions and go straight to the ones that we may need to review. Now, the idea of pure substances versus mixtures, I think, is something that is better if you memorize the distinction. Now, when you have pure substances, you can have elements. An element is something that appears on the periodic table, and compounds. Compounds is something that has a chemical formula. H2O would be a compound, not an element. It does have two elements, hydrogen and oxygen, but it's a compound. So if it has a formula, it's a compound. This is not a formula, it's a chemical symbol. Appears in the periodic table. That's the same thing, that's the same thing. So the only one in these four choices that has a formula is that octane, the gasoline. So you probably knew that. Pure substances can be compounds or elements, but not mixtures. You know, the word soda, I guess this country is big, so some people call it pop, right? Or soda pop. So that's what they're talking about here. This is what I consider cultural bias, if you will. I mean, not everybody's going to know. Certainly not in Jamaica, right? What the heck is a soda? What do you call a oh, a soda? Okay. Anyway, my point was that in some places they call it pop. And so this is biased against those people. My wife from Minnesota says pop, not soda. In the South, they probably say soda pop. I have no idea.
They call it Coke down there.
Yeah, I know. Yeah.
Everything?
Pretty much everything, yeah.
Everything. Don't matter if somebody says I'll have a Coke, you gotta ask them what kind.
What kind, yeah.
Oh, wait.
Absolutely.
Yep,
Yes.
In the South,
Yes.
everybody calls it Coke.
It's true.
In Louisiana, at least, if you say tea, it does not mean hot tea.
Oh, yeah, you shared that with me last week.
So 5 years to figure it out. Now he says iced tea. But
Yeah,
down
yeah,
there,
yeah.
They give you a tea before you have to ask for water, but they automatically give you tea.
It's just the same in some other places. So in northern Mexico, if you ask for a lemonade, they give you a lemonade, right? But if you go to Mexico City and you ask for a lemonade, they're going to ask you what flavor. It can be actually a banana lemonade. And it's like, doesn't have any lemons, but it's a...
And I get one more fact, just like culturally how things are different. I thought it was out of this world, but down there, like in the podunk, like pizza, they have sorry, they
It is
have
very-
daiquiri drive-throughs.
Oh, really?
Alcohol, yeah.
Wow.
And so it was a huge culture shock when he came up here that you can't just go to these sporting goods and leave them done. But down there, you how they get away with it is they have a special cup and it's whatever daiquiri you want, all alcohol. It's not drinking and driving because they take a piece of masking tape from and they put one piece of masking tape over it. And so if the cop pulls you over and that masking tape is broke, you broke the seal. And so that
That
you get in
means they...
trouble for an open container.
The only thing is it's not hard liquor. By law,
Right.
they say it's hard liquor, but it's a wine-based daiquiri that you can get in drive-throughs in Texas or anywhere in the
Oh,
South.
yeah, in
Yeah,
Texas,
it's
too,
so
yeah.
cool. I thought it was like there's no way. I mean,
Game changer. I'm getting a drippy nose, and it's nothing to do, so I'm going to put this thing on to test myself. Okay, so let's take a look at this. So the reason I mentioned the soda is because actually bicarbonate sometimes is also called soda, and that would be a compound. So my apologies for this cultural bias and also for this ambiguity. So which of these is not, which of these is a pure substance?
Sugar.
The gold.
Gold. Wait, a pure substance?
Yeah. So we need
I
to,
put sugar in it, it was correct. Pure substance. 14K, that's not pure. Isn't it?
right, 14K gold, that's a tricky question. It's not pure, it has other stuff.
It's not.
Right, it's not pure gold. I think 24 is pure gold. But that's assuming that you know the definition of carat, the K. So I'm sorry, this is a bad question. So what was the answer you think?
Sugar. Sugar.
So this is a mixture, obviously.
Sorry.
That they're talking about a drink. So it's a mixture. That is a mixture as per our understanding of 14K versus 24K. And that's the only one with a chemical formula. They should have put it in front of it. Yeah. Because if you say like raw sugar, then it has a little bit of other stuff. Well, if you lose points here, just let me know. Okay, I think I can skip this. Any conversion of temperature, guys, please don't even do it by the formula that the book has. Just ask a smartphone, a speaker, Google it. We're not going to go there. I mean, I used to know how to do it and I would do it, but now I just ask my speaker at home, what is 50 Celsius in Fahrenheit? And that's it. And that's not cheating. Okay, so chemical changes and physical changes can be a little ambiguous. Remember, if the product of the change is permanent, it's chemical. If you can reverse it, it's physical. Okay. Do any of you make compost at home? Compost. That word right there. Do most of you know what compost means? So compost is when you take organic waste. By organic, I don't mean organic in the sense of the grocery store, but organic by containing carbon, and you let it decompose in nature. So composting something is breaking things down into the original components, if you will. So no need to go there. Potential energy versus kinetic energy. Kinetic energy is always energy that involves movement of some sort. Potential is stored energy. So chemicals, like sugar in that question before, have potential energy, not kinetic. Unless you heat them up and they start boiling, then there is kinetic energy in there. So just keep that in mind. There's a subtle difference.
Would that be calories in a hamburger? The answer.
So let's see which ones don't have movement. So walking a dog has movement, right? Kinetic.
Throwing a baseball.
Throwing a baseball, there's movement there, so kinetic. Pedaling a bicycle, there's moving in the pedaling, so kinetic. Calories in a hamburger is built in there. The calories are not moving until you eat it, and then they become kinetic energy because you start getting anxious from all of those calories. So yes, that would be potential.
Can you do that next problem? 3.27.
Yes, let's go down. Yeah, so these are the ones that I think require a little bit of remembering that those two formulas that we had. Okay, so let's put the two formulas back. Specific heat and then Q. So specific heat was defined as the amount of heat required to raise the temperature of 1 gram of substance, so mass, 1 degree Celsius, so times delta T. That's the first formula. The second one just comes from here, so we're going to move that to be with SH, so it's SH times M times delta T. So maybe I should put parentheses here. The parentheses are, in this case, the way in which I indicate multiplication. Now let's see what information we have. So the energy needed to keep a 75-watt light bulb burning for 1 hour is 250 kilojoules. Okay. Let me put all the information on the board. Now, we have nothing that relates 75 watt to anything in this formula. 75 watt is power. Now, we don't have to dissect that. We're going to use conversion factors to address this problem. So we know that this equals, and we're going to put the number of joules, 250 kilojoules, per 1 hour. I'm going to erase the 1. I'm just going to put it per hour. So this is an equality, right? If I raise the 1, nobody will object, correct? There's always a 1. If I say 50 kilometers per hour, I don't have to put the 1 right there. You know, or 60 miles per hour, I don't have to put the hour there. I mean, the 1, I just know that it's per hour. So the same thing goes here. This is 75 watts per hour. This is an equality, right? Every equality gives you conversion factors. If you want the energy, you want kilojoules. Kilojoules are a unit of energy. So calculate the energy required to keep the light bulb burning for 4 hours. Okay, so we want 4 hours multiplied by a conversion factor that comes from this equality that cancels everything except the kilojoules. Okay? So what are the two conversion factors here? So if I put 250 on top per 75 watt per hour, I end up with a problem because I have watts involved there. But let's use logic. Just approach this problem logically. You know that in 1 hour, this light bulb is going to use 250 kilojoules. So really the question is so straightforward that makes sense to just not pay attention to the light bulb. I could have said a pink light bulb burns 250 kilojoules in 1 hour. The 75 watt is just the description of the light bulb, not necessarily the power that you require. So with that, we're going to ignore this. I'm just going to call it light bulb. That's a light bulb. And I'm going to multiply the two numbers, which is going to give me 1,000 kilojoules. Think about it. So you have a 75 watt light bulb. We don't care about how many watts we're using. We just care about how much energy that is burning. And that is 250 kilojoules in 1 hour. So in 2 hours, 500 kilojoules. In 3 hours, 750. In 4 hours, 1,000 kilojoules. Now we have an answer that we need to convert to the different choices here. They want the answer in joules and in two significant digits. So we have 1 kilojoule equals 1,000 joules. We need to convert this number to joules. So we're going to multiply that number by a conversion factor that comes from here. So 1,000 on the top, 1 kilojoule on the bottom, and that will be 100,000, no, 1 million. Well, that's a tough question because how do you write that in two significant digits? How do you express this number in two significant digits? That has one significant digit, and we cannot do any more than that, right? That's a tricky one. Let's see what they want. Right now, I don't think I can solve it because I'm in the print view. Let me go back and open it from the real question. Which one was that?
Number 13, problem 3.27, the one that we just worked on.
Right here, okay? Oh, number 13.
Number 13, that's number 9.
10, 11.
13, problem 3.27.
Okay. I'm very curious about this, so I cannot do that to two significant digits. So let's see what is the answer. Ah, with scientific notation,
I'm pretty sure if you put it in the other way though, it would automatically mark it right, because that's happened.
which is what I did. I put a million without, so yes,
So it doesn't matter really.
it doesn't matter really, that's the bottom line. So this number, if you really want to emphasize two significant digits, we cannot do it in decimal notation. I mean, this has one significant digit only. So we have to go, okay, let's turn this into scientific notation. The decimal point imaginary is here, so it's 1, 2, 3, 4, 5, 6. So it's 1.0 times 10 to the 6th. Here is where the two significant figures is. If you need 3, you add another 0. If you need 4, 1.000 times 10 to the 6th. These are all the same number, but with different number of significant digits. This is the only one. This is the only one with 2, and that's what the problem just converted that to.
So I have a question.
Yes.
Mine is a different problem.
Okay, let's put it on.
5 hours. So my answer is 1, 1, 2.
It's 14. with
So it's the same
after that.
250 kilojoules?
Yeah, still 250 kilojoules, and then times I get times 5 hours instead.
So that's what you start with 1,250 kilojoules?
I started with, no, that was my answer that I got, was 1,250, because I multiplied 250
Times 5.
5.
Okay. But then they wanted joules or kilojoules?
They want the same thing, kilojoules.
Kilojoules, okay. Then 1,250 is the correct answer. However,
Oh wait, I lied. They want joules.
so if they want joules and they want two significant digits, we first have to do the same conversion. We need to multiply these by 1,000 joules per kilojoule, which give you 1,250,000 joules. And now if they want two significant digits, I guess we have two choices here. And I'm glad we looked at the scientific notation, because this one we can actually write in two significant digits in decimal notation. So I need to drop the 5. This is going to turn into a 3, so it's 1,300,000 joules. So let's move on. Now we have to convert the same answer to kilocalories. You know that for that you have a conversion factor, so I'm not going to do it, okay? It's the 4.184 or something like that. Or do you want me to do it? There's a conversion factor that we learn. I don't have it here, but I can always.
4.184, you're right.
Yeah. So, and which one is which? 1 calorie?
It's
4.184 joules, or the other way around? The other way around, right?
joules.
Help me out.
Calorie equals 4.184 joules.
Okay, 4.184, yeah. So using that equality, all we're going to do is convert the number that we have here to calories. So in that particular problem, 1.0 times 10 to the 6th, these are joules, times 1 calorie divided by 4.184 joules. Cancel joules out, and you have your answer in calories, whatever the answer may be. I don't mean to rush. I just think that these are things that you probably feel comfortable doing already. But if you want me to do any of these problems, I can certainly do it. And then the last one is in kilocalories. Actually, this is in kilocalories, not in calories. Let's just take a look at another one. because I think we need to use that equation in some of them. So this is a generic question. No calculations needed unless you think that you need them. And you need to determine, using specific heat, which of these substances. So if the same amount of heat is applied to samples of 10 grams, all of them weigh the same, of iron, silver, and titanium, which sample would reach the highest temperature? So you have aluminum, iron, silver, and titanium. Iron, silver, and titanium, the bottom three. You look at the specific heat. You need more heat to heat up the substance with the higher specific heat, right? So you need to use more energy to raise the temperature of titanium and less energy to raise the temperature of silver. So the question is, which sample would reach the highest temperature? We're heating the same amount with the same energy. Excuse me. Well, what do you think? Is it going to be silver? Is it going to be titanium? Is it going to be iron? So what is it?
It's going to be the gold.
Oh, but in this case, there's only those three.
That question is iron, silver, and titanium.
Oh, okay.
Yeah. So let me take a go. Yes.
But of the
If it was all of them, it would be gold. You're absolutely right.
it'll be silver.
So we silver.
Of the three choices, it would be the one with the lowest. So it will get hotter because it requires less energy to raise the temperature of the same amount of. I mean, you can do it numerically, definitely. Let's do it for two of them numerically, just to make sure. So we have 10 grams. We're going to be solving here anywhere for delta T. Okay? I'm gonna get into a rabbit hole here, but I'm going. I'm gonna do it. So I'm gonna solve for T here. I'm gonna move this to this side. So Q divided by specific heat times mass. All I have done is modify this equation to have a new equation in terms of temperature, because I want to see which temperature delta is the highest. And I'm going to only do it for two of them. Let's do it for the one with the highest value of the three, so iron, silver, and titanium. Let's do it for titanium first and see what happens. So the delta T for titanium would imply for us to put, let me see. We're going to put here Q. We're going to put here a specific heat, 0.523, and the mass is 10 grams. And then we're going to put here Q, and we are going to put the other two numbers, 0.235, and then 10, because those are not changing. Q is also going to be a constant. So let's see. What is that times that? Q divided by 5.23, right? What is this times that? 2.35, right? Now let's look at this for a second. So this Q, we don't know what a value is. We can put any number that we want. But what I want you to see is that if this is 100 and you divide it by 5, and this is 100 and you divide it by 2, one is going to give you a bigger number. And the bigger number is going to be this one. You're dividing the same amount of heat by a larger number here, so you're going to have a less increase in temperature. Here you're dividing it by a smaller number, so you're going to have a higher increase in temperature. We don't even have to put numbers. Okay. So we said it was silver. Next one. Please do stop me if I'm not making sense, you guys. Sometimes I wake up more inspired than other days. I'm only human. So I need for you to tell me or give me feedback if what I'm writing down, if I'm trying to explain something and it's making no sense, you need to stop me. As much as I would love, I cannot really read everybody's mind. And I don't mean that in a bad way. I really mean it. I want everybody to feel comfortable enough. So let's take a look at this problem. Use the heat equation to calculate the energy in joules for each of the following. The heat equation is this one, the second one that we have here. And we have numbers on the problem and a table. The table have the values of SH. So the table has these values right here. The problem itself provides you with conditions of a mass and a delta T. And remember what I said earlier. The book doesn't care about the sign, but I kind of do. The delta T is always the final temperature minus the initial temperature. Sometimes you may see it in books as delta T equals T2 minus T1. That just means final minus initial. So for the first problem, we are going from 13.5, that's the initial temperature. So delta T equals, the initial temperature is 13.5. To what final temperature? 24.7. In this case, we're adding heat, so we're heating up, so it's going to be a positive delta T. We're not removing heat like when we were cooling the patient last time. Remember we were cooling down somebody? So that's why we got a delta T that was negative, because we were going from high to low. Here going from low to high. So delta T equals whatever that is, 11.2 maybe? Please correct my math. It is correct? Okay. So we have 28 grams of water. We're going to use this equation. Q equals 28.0 grams times 11.2 degrees Celsius. Now what goes here? Whatever the specific heat of water is according to this table.
Which one? There's two.
Say that again, I'm sorry?
If you scroll the table all the way down a little, no, yeah, it said there's two of them. Which one?
Ah, yes, that's a very good question. Well, what temperature are we at?
We're at
Water is liquid at any temperature above 0 degrees Celsius and is not a gas below 100. So we're going to use L.
okay.
This is something that you haven't learned in this course yet.
Okay, I get it, but then which one do I choose?
Right. In a future chapter, which is coming up very soon, we're going to learn how to write chemical equations, reactions, if you will. And in those chemical equations or reactions, we're going to have to write the state of matter, the physical state of matter. There are 4 states of matter that we're going to learn about. S is solid, L is liquid, G is gas, and then there's one more that doesn't show up there, AQ, which means aqueous, which means in water. So solid, liquid, gas, and aqueous are the states of matter that we're going to be dealing with. So very good question right there, because, yeah, we don't want to use the solid specific heat of water. That's for ice. We are in liquid water because of the temperatures that we were given. So 4.184, what are the units? Joules per gram per degree Celsius. So we're going to get our answer in joules. What was it? 184. That number looks familiar, right? Because that's the equivalency between calories and joules. So if we multiply those numbers, we should come up with the correct answer. Now the units of these are going to be units of heat, which are going to be units of joules or kilojoules. I didn't put them there. Let me add them up. Joules per gram degree Celsius. It's easy to erase when you have an erase board, a dry erase. I'm sorry if you have to scratch your numbers on your piece of paper. So let's take a look at the units. Grams and grams cancel out. Celsius and Celsius cancel out. We're left with joules, which are units of energy. So whatever that number is going to be our answer. If you don't mind, could you calculate it, and let's talk about significant figures when you give me the number?
1,312.
What was it, 1,000?
1,003, or it looks like that actually, from my calculator, but 1,312.1024.
Okay, just read one digit at a time.
1,
3,
3, 1, 2.
and then point.
0.1024.
Thank you for doing that. Thank you for including every digit that your calculator is giving you, because we need to continue to feel comfortable with significant digits. So that's the calculator answer, right? Did they ask for a specific number of significant digits? They don't, but we know better, and we know that we need to fix this answer to the number of significant digits that we have here. So 1, 2, 3, 1, 2, 3. We're going to reduce these to 3 significant digits. Are you getting a different number when multiplying? I have the decimal in the wrong place. So I need 2 confirmations. I have 2 different ones right now. Can somebody else multiply 4.184?
Unless I can't see.
Oh, 4.184 times 28, so that's about 100 and something. So it's going to be in the thousands, yes.
Yeah, it's 1312.10. Yep, that's the correct answer.
Okay, so now I have 2.
No, the decimal is in the wrong place.
It's 1312.
I don't think it's in the wrong place. I don't think it's in the wrong place simply because that times that is 100 times that is 1,000. So it's going to be in the 1,000. Where you think is the decimal point? You think is here or there? Take your time. Sometimes those screens are so small that you don't see the. Let me take a look. You're getting 13,000?
Unless I'm just going to use my calculator.
Okay.
not my phone.
All right, so let's assume that this is right for a second. The computer is going to tell us if it's not. We decided we need to reduce this to 3 significant digits. What is your suggestion? What do we write instead of that number? 3 significant digits. This is 1,312.1024. We need 3. 1310.
Zero.
That's it.
Because it needs to be 3.
Correct. It has to be 3 significant digits, but it has to be in the thousands.
But
It can.
will accept that answer and then convert it for you.
Oh no.
Yeah.
Well,
Yeah,
okay.
because they didn't specify how they want the answer. So you submit that, it will say it's correct, and it will give you the
Okay. The correct answer.
yes. It's
Well,
correct.
Because you are so good and you know that you can get significant digits all the time correctly, always go by the data that you are given.
Okay.
I mean, that's just the safest thing. So the units are already indicated in the problem, so you don't need to type J in front of it. Let's just submit it. And in this case, it didn't have to change our answer to something else because that's exactly what we provided, right? But I get what you're saying. It would have changed it.
And you just put it like that, it will convert it.
Great. Okay, now let's take a look at part B. It's the same thing with a different temperature range. So I'll let you practice that on your own. Because we have only 15 minutes left. I don't want to run out of time. Let's go to the next problem. So it's the same type of problem.
Yeah, but this time they're asking for you to input the answer in 3 significant figures.
Oh, now they are
Now
asking
they're
for.
asking you.
Okay, perfect. But it's the same mechanics. You use the same formula that we've been using. Now, this is interesting. Let's take a look at part C, because they're talking about energy lost. And I don't want somebody struggling with this problem later. I'm going to set the record straight, maybe by making a mistake. So when you talk about loss of heat, in my brain, I immediately think negative number. So the question I have in my mind is, am I going to supposed to write the negative sign in that answer, or is he going to assume that the negative sign is understood because of the energy lost point? So let's take a look, and let's just do it. So same formula. In this case, we have water still in the liquid state. So we're going to have 4.184. I'm going to skip units this time because we already know that the units work. 76.6 grams. And then the delta T is going from 86.4 so that's the initial temperature, that's why I'm putting it last, to 3.4. So remember, this is final temperature, this is initial temperature. So the delta T is going to be a negative number, right? Because it's an energy loss. Negative 83. So if I put negative 83 here, my answer is going to be negative. Now please do the math for the class, if you don't mind. 4 times 80, 320 times 80, 20. It's going to be like 24,000 or something like that, or somewhere around there. I'm waiting for anybody who wants to contribute this. I do have a calculator, but I think I know how to do it, so
It's 26601.0352.
Okay, I like that because I was in my brain doing about 24,000, roughly speaking. So 26,601.0352 negative, because that's a negative value there. Negative times positive is negative, negative times positive is negative, so negative joules. Now, they want what? 3 significant digits? Or they don't mention that?
I think
Yes, 3. So let's turn this into 3 significant digits. What do you think that is? 2, 6 has to stay, 6 has to stay. We drop that 0 because that's 3 significant digits already. Now this is 26,000, so 266 makes no sense. We need to add placeholders, zeros, until we get to the 26,000 range. So that's 2,000, that's 26,000. That should be the answer. Those zeros are only placeholders. So I'm going to put the negative sign and see what happens here. Okay, let's see what it says. Oh, actually it explains that the negative value, which they do add. So shame on me for not entering the number as positive, which would have given us a feedback as to what happens if you put a positive number. But now I at least know that it is expecting a negative number. Okay, one more problem before we had to go, I think. And I want to see one with specific heat. Oh, so this is a word problem. This is super important that we do together because it's a multi-step problem that you need to rationalize. So let's read it carefully and see if it can be translated into something simpler than this long sentence. All the heat lost by the metal, oops, I guess I'm not seeing the original problem. So we have an 80-gram piece of copper metal at 54 degrees Celsius. And you drop that into 25 grams of water. So we have a beaker. There is water here. There are 25.0 grams. And they give us a temperature of that as 26 degrees Celsius. I'm dropping a piece of metal, which is copper, symbol Cu, with a mass equals 80 grams, so 2 significant digits, and the temperature equals 54 degrees Celsius. What is going to go on? Think about this mental experiment. What's going to happen to the water temperature when you add something hot to that water temperature? It's going to go up. What is going to happen to the temperature of copper, which starts at 54, when you put it in the cooler water? It's going to go down. They're going to reach an equilibrium at one point. In other words, a temperature at which both of them are at the same temperature. Now, here is where the problem comes into place. All the heat lost by the metal is used to heat the water. And the final temperature of the water and metal is 29.2. So we have a TI, initial temperature, and a TF, final temperature, which is 29.2. the initial temperature and the final temperature is going to be the same. Now, can we calculate a Q for anything in here? Can we calculate a Q? So what do we need to calculate Q? We need specific heat. Well, we're given the specific heat of water. We don't have the specific heat of copper. Although we know that is there because if we go to another problem, we can find it. In this problem, it's not there. So basically, what we can do is calculate the amount of heat, Q, gained by water. So step number one. Is everybody following my logic here? Because it's not my logic, but it's the logic that exists for this problem. Because the amount of heat that the water is going to absorb is equal to the amount of heat that the copper is going to lose. We can calculate the specific heat of copper using the fact that we know the specific heat of water. So first, we're going to calculate Q for water in this problem. I'm going to use the 3 minutes that I have left. I'm so sorry. So Q equals specific heat, 184. I'm not going to put units just to save time, times mass, 25 grams, times delta T, oh my goodness, that is 3.2. And what is the sign? Final minus positive. So we gain heat. So what is that? 4.184 times 25 is 100 and something.
334.72.
Okay, I'm sorry.
334.72.
And these are joules. Now, step two. Now that we have Q for the water gain, we're going to assume that that's the same Q that this guy is going to lose. So calculate SH for copper using Q of water above. So SH equals Q, this is what we're using, 334.72 divided by mass. We're using now the mass of the copper, not of the water, because that's what we're cooling down. 80, and then divided by the change in temperature, which is going to be a negative value, which in this case we're actually going to ignore because this Q, well, suffice to say that the negative value is not going to be reported in the specific heat. You're going to get rid of it. So what is that delta T?
Negative 24.8.
-24.8. So if we do those calculations, do we get a number similar to, let me see, 0.385? Is the answer that you're getting somewhere around that neighborhood? So you're calculating this, 334.72 divided by 80, and then that divided by 24.8. We're going to have to start this problem again on Thursday. I don't want to rush it.
0.1687.
0.186, that doesn't look close to copper. So I don't want to hold you and make you late for another class. Let's pick it up here on Thursday. We'll go back to this problem, and then we'll wrap up chapter 3.